Sorry about that. I guess I'll start over. So I don't know if anyone got the beginning of what I was saying, but we'd like to welcome you back. We were with you just a few minutes ago for the first session dedicated to AI and meteorology. My name is Anne Dacres, and accompanying me is my co-host Miguel Tremblay. We both work for the Meteorological Service of Canada within Environment and Climate Change Canada, and we're here with you for a second year exploring AI. But before we begin, a few reminders. We've reserved 15 minutes for each presentation, and we're asking presenters to keep 3 minutes for questions at the end. So time permitting, attendees will be able to post their questions in the Q&A you'll see on your screen. Miguel will provide a heads up at 10 and 12 minutes, and we'll bring the presentations to an end at 15 minutes. And we'll be ruthless because we want to make sure everyone has time to present. Miguel, you want to translate that?
Ouais, mais je vais y aller de façon plus rapide. Donc, Miguel Tremblay avec Anne Dacres, notre deuxième année pour faire une session sur l'intelligence artificielle. On travaille tous les deux au Service météorologique d'Environnement Canada. Donc, on va faire ça 15 minutes, 10 minutes de présentation, à 12 minutes, on arrête pour 3 minutes de questions. Voilà, c'était un peu ça que j'avais à dire. On prendra pas plus de temps parce qu'on a déjà mangé 2 minutes de ce qui se passe. Si vous avez des questions, allez dans le Q&A dans Event Mobi pour les poser, s'il vous plaît. Et gênez-vous pas pour en mettre beaucoup, là, on aime ça. Voilà. Donc, sans plus attendre, je vais poursuivre avec, en présentant Christopher Subich, encore, qui va nous présenter Why are AI forecasting models so fast? Je vous pose la question. À toi, Christopher.
There we go. Let's unmute and I can start. Greetings. Welcome back, everyone. I'm still Christopher Subich, and this time I'm here to talk about the performance aspects of machine learning forecast models. In particular, well, AI forecasting is new, it's impressive, it's scary, and there are a whole lot of promises. Every single one of the published AI forecast systems has promised some kind of state-of-the-art performance with orders of magnitude faster running times than traditional models. And I'd like to start picking at those performance claims. In particular, because I have to narrow things down, I'm going to look at the medium range forecast models that are out there, in particular GraphCast, which is a quarter degree global atmospheric medium range forecast. Now, all of these models, GraphCast included, has a limited set of model levels, output times, and variables, so it's not as complete as a traditional NWP system, but there's a pretty common assumption, you might have heard it in the plenary, that it's only a matter of time before these forecast models take over everything and regain missing capacities or come up with entirely new ones. So, here in this talk, I want to narrowly examine the performance claims of GraphCast compared to our operational forecasting program GEM. Other people have talked at great length about the accuracy. All of the preprints talk about accuracy. That's a moving target. That's not what I'm here to talk about. But instead, what supports the speed claims? Because to my mind, there are three possible answers. The first is that they are somehow doing a better job at representing the Earth system, and they've learned something that our models just don't have. Another option is that they're just really good at running on GPUs, and if we could get our models to run on GPUs, we'd catch up. And the third option is that the AI models are, in some sense, cheating because of their sparse outputs. And the answer to these questions affects the long-term future of traditional NWP. If the AI models are truly better at representing the Earth system, then there may not be a bright future for traditional numerical weather prediction. On the other hand, if the AI systems are going to lose ground when we ask them to produce dense forecasts, then the traditional NWP picture looks a lot better. So, for this talk, GraphCast is being taken as typical of all of the machine learning medium range forecast systems ever. It was open sourced last August by Google DeepMind. It's a quarter degree forecast that forecaster that produces forecasts 6 hours at a time. It runs on among 37 pressure levels, which is the version I'm using. It predicts wind, temperature, geopotential, and humidity. And it was run here on a GPU for a single 40 gigabyte A100. It's a graph neural network architecture which has a 1 degree internal icosahedral mesh. and a quarter-degree lat-long encoder and decoder layers at either end. In our corner, representing traditional numerical weather prediction, is the GEM forecasting model. I picked a 1/3 degree global configuration because I could steal it from the operational ensemble forecast. This configuration has 84 vertical layers, giving it a similar total number of grid points as the GraphCast configuration at 37. It runs on a 15-minute time step with all of the physics parameterizations used in the ensemble system. And I ran it on a single compute node of 80 CPU cores, and internally it has semi-Lagrangian advection, Craig-Nicholson time stepping, and an inner Fourier solver for the inner linear problem, and all sorts of bells and whistles. I asked both systems to produce a 24-hour forecast for a particular date that isn't terribly important. And I chose this because it's the closest reasonable comparison between the systems, but it's admittedly not exactly equal. GraphCast, as mentioned, has a slightly higher horizontal resolution in this configuration, but GEM has a much higher vertical resolution and a shorter time step. That shorter time step is necessary for stability, but on the other hand, it means those outputs are basically free. So if I want a 1 hour, 15-minute field, I can get it. The physics parameterizations being run meant that GEM tracks about 200 variables internally, between the dynamics variables and things like the turbulent kinetic energy and cloud water fractions and variables that are just not explicitly represented anywhere inside GraphCast. And in operations, GEM would normally run on many more nodes than just one, but one node here was the closest hardware level comparison that seemed reasonable. For this work, I measured the overall wall clock time and the computation time, which excluded the I/O, and I measured the floating point operations executed, as well as the amount of memory accessed. This lets me take advantage of what's called a roofline model, which allows me to compare the models not strictly to each other, but to the peak performance possible on their system. The idea of this model is that floating point operations represent the real work done by the model, and the memory accesses are the cost we have to pay to have data to work on. Now, since computers can do both these things at the same time, in the schematic view, the maximum runtime of the model runtime is the maximum of the memory read divided by the memory bandwidth, and the flops divided by the compute rate. This is an idealized model, but it's remarkably close for at least order of magnitude comparisons. It's called a roofline model because if you plot the system capacity on a log-log plot, it looks like a roofline. On the left side, you have memory-bound algorithms. On the right side, you have compute-bound algorithms. Memory-bound algorithms would be faster if you had faster memory. Compute-bound algorithms would be faster if the CPU could do more work. These tests were run on one of the nodes of the ECCC supercomputer. The compute nodes are 80 cores of Intel Xeon Platinum processors, and the GPU nodes have 4 NVIDIA A100s, of which I only used one. Now, measuring the performance of the system, one CPU has a maximum compute rate of about 150 gigaflops per second. If you extend that to a full compute node, you get not 80 times better, about 50 times better at 77.4 teraflops per second, but the memory only gets 12 times faster. The upshot is that on a compute node, you need to do more compute per byte of data in order to fully utilize the computation power of the CPU. On a GPU, these numbers all get better in a similar sort of scaling relationship. When you include the tensor cores in the A100, one single A100 GPU has 310 or so teraflops per second of compute capacity, which is about 40 times the performance of an entire compute node CPUs. When measured against the high bandwidth memory on card, it also has about 1.3 terabytes a second of memory bandwidth. Now, while these are all better than the CPU node, again, the scaling still favors more and more compute intensity. You now need up to 240 floating point operations per byte of data to truly utilize all of the compute that a GPU gives you and to become compute bound. We don't want to be memory bound. We're leaving the expensive hardware somewhat idle if that happens. Now, in terms of where our systems show up on these charts, GEM takes about 150 teraflops to compute a 24-hour forecast. but its compute intensity is pretty low. It only does 2.6 or so floating point operations per byte of memory accessed. That means that on one compute node, it takes about 10 minutes for the forecast, of which just under 9 minutes are core compute time. And compared to the capability of the system, it's pretty clearly limited by the memory bandwidth. Now, GraphCast can run, is designed to run on GPUs, but you can make it run on a CPU. And if you do, on one CPU, it will produce a 24-hour forecast in about 21 minutes, of which 20 minutes or so is compute time. That's slower than GEM on a full node, but that's still frighteningly fast for a one CPU configuration. On 80 CPUs, it computes the forecast in about 90 seconds, of which 80 are core computation. Both of these configurations involve GraphCast executing about 32 floating point operations per byte, so a full order of magnitude more than GEM. Consequently, the model sits much closer to the compute bound limit on CPU, which isn't even what it was designed for. On 80 CPUs, it suffers because it's not truly that parallel. Now, if you run GraphCast on GPU as it's designed, it computes the full forecast in 25 seconds, of which only 3 seconds is the core computation. The rest is data reading and writing, mostly. And at the mixed precision it was running on, that meant it was running 154 floating point operations per byte. On CPU, GraphCast is compute limited. On a GPU, it is pretty darn close. And frankly, 3 seconds of core computation for a 24-hour forecast versus 9 minutes is an impressive ratio.
Christopher, 2 minutes?
Yep, okay. Now, all that being said, GraphCast is frighteningly fast, but it's not really doing less work than the traditional NWP model. 110 teraflops for GraphCast is a large proportion of the 150 used for GEM. So that's with a comparable number of grid points, so in some sense a comparable amount of work, even if GraphCast simulates fewer variables. If you decompose that speed advantage, you get a factor of about 1.4 from fewer flops, a factor of about 5 from the better compute efficiency, and a factor of about 25 from the GPU, for a net speed advantage of a factor of 170. Now that 3 seconds per forecast is almost impractically fast because it ends up being dominated by I/O rather easily. And as a digression, that means we need to, going forward, have some focus on high-performance parallelizable file formats. But to return to the questions from the beginning, have the machine learning forecast systems learned a more efficient weather representation? Probably not. Interpretability is still hard, but there's no real evidence that GraphCast is doing more with less, and I expect the other forecasting systems would show similar results. Are they good at running on GPUs? Abso-freaking-lutely. The GPU advantage alone gives GraphCast more than half of its 170 factor improvement, but that's enabled because GraphCast has a much better compute intensity than GEM. So if we had a mythical version of GEM that ran on a GPU, we would not get that factor of 25, we would be something substantially less. But are the reports misleading because the machine learning systems do less work? It's probably not, but there's room for discussion here. A factor of 170 is a lot, so even if we give back an order of magnitude to have more outputs or an ensemble or something, that's still much faster than GEM would be. And there's still open questions about model capacity. For example, how much more can GraphCast or a model like it learn without needing to become larger and a little bit less efficient? So overall, the story I think is fairly encouraging for traditional numerical weather prediction, which is weird coming from the AI session, but it's my true feeling. On the traditional NWP side, I think we leave a lot of compute capacity underutilized. We are paying for CPUs in some sense that we aren't using. If we kept the same memory access patterns, GEM could do an order of magnitude of more compute for basically free. It's hard to retrofit this onto current models, but I think this is an important consideration for next generation dynamical cores and physics parameterizations. For a machine learning model, everything is a matrix multiplication. So maybe we need to look at, for example, very high order dynamical cores to get some of the same edge. AI models are designed around accelerators from the start, so obviously they're good on GPUs, but they have their own challenges. We haven't really seen weather models scale up to the level of GPT-4. And they're going to have to tackle the problems of large-scale cross-node GPU parallelism to be equivalent in size. high-resolution global multimodal weather data is a really large amount of data, and just handling that is a problem. The Microsoft's Aurora paper, just recently released, takes great pains to note that its training was bottlenecked more by I/O access than by GPU compute, and I think that's a trend we might see in the future. Okay, thank you very much. I'm happy to take questions.
Merci. You know when you see my face that it's over, Chris, do you?
Yeah.
Yeah, I was a question for you. So, you talk about the time and the number of flops, but does it translate into directly, more or less, into energy saving?
Ooh, within hardware, yes. The GPUs and the CPUs both are in their highest power modes when they're doing the numerical number crunching. Between GPUs and CPUs, it's a little more nuanced because GPUs tend to be more energy efficient per flop. But when comparing like for like, when comparing an AI model to an AI model and a CPU model to a CPU model, yes, energy would more or less scale.
Yes.
Um,
Maybe one last one. How would you factor in AI model training? Does it dwarf compute cost of running?
Okay, that's a good question. GraphCast took about a GPU year to train. It would take about 30 seconds at this rate to produce a 10-day forecast. So if you train GraphCast once, then yes, you would probably take a long time to pay it back. On the other hand, if you take GraphCast and you're running a 100-member ensemble, then you're paying that right back. Realizing that compute clusters abhor a vacuum, I have a strong personal suspicion that while there are AI training costs, I suspect in operational use, we will see a large fraction GPU utilization just from operational running models, because it would be a shame to leave resources idle, and if nothing else, people are going to scale up systems or start running larger ensembles, just as they do with traditional NWP systems.
Thanks for your answer, Christopher.
Mm-hmm.
We're going to have to move on. So I'm going to ask Dominique Brunet, who's research scientist with Environment Canada, who's presenting towards state-of-the-art nowcasting with a foundational AI model and ECCC-IBM collaboration. So yes, I see you're already setting that up. Thank you, Dominique, and I'll hand the mic over to you now.
Thank you. So yes, I'm a research scientist at Vikram Khade. This is a collaboration with IBM. So what it means basically is that IBM did a lot of the work, and then we're taking a lot of the credit. But Aliana will show like how this collaboration can really work together. So the problem we're trying to answer is the classical nowcasting problem, which, if you're not familiar with it, it's basically taking radar precipitation estimate from the past and then trying to forecast, or let's say nowcast in the future. So what will be the future radar echoes in the next hour or so? So in America, what we're using currently is based on PyStep. It's called smooth feedback algorithm, and what it does is it finds the motion from image to image and then advect it forward. So it's a simple Lagrangian of the motion inferred from the past images. And what was before AI, so maybe in around 10 years ago or so, we had NLP, for example, a rapid update called HER, which is what is state of the art for short lead time. And then the PySteps method, there's many methods in PySteps, but most of them were about 2 to 3 hours the crossover. So basically, before the first few hours, nowcasting was better, and then after 3 hours, the NLP will be better. And then this is true for medium precipitation, so 2 millimeters per hour, and then also for higher precipitation, so 20 meters per hour, which the lead time also about 2 hours and a half. And AI didn't start 2 years ago. There was early AI development, for example, RaiNet, in about 2017, and it was a slight improvement in performance for medium precipitation. but there was some issues with high precision because of the earlier model based on CNN or UNet tend to smooth and dampen the signal so that you don't get the high precision. Then what we call the AI revolution, which happened about the same time or even a bit before GraphCast, so starting in 2020 with DGMR, and then more recently nowcastnet and MetNet, get the performance crossover at 6 hours for the medium precision and about 3.5 hours for high precision. And then because they are generative AI, there's no smoothing of the high precision, or really little smoothing of the high precision. And didn't stop like with the first generation. There was rapid development. So 2020, 2022, 2023, there was 3 different models from Google, and the performance is quite incredible because in 2020 was about 6 hours lead time, then it moved to more than 12 to 24 hours. That the crossover between NLP and nowcast. So I didn't show like, but it's about 18 hours. And then went for high precision, also get good performance. So which is very interesting, very important for helping for the warnings. So nowcasting now is better than rapid update NLP for the first 24 hours. So this is for precipitation. So the goal of the project is to implement an nowcast AI model on our data, on our infrastructure in an operation-like environment. So we really wanted to help to get this innovation in Canada. So aim to get a state-of-the-art performance in Canada with exponential development, and also gain knowledge of how to do AI by collaborating with IBM. And that's few stretch goal, which is to go from only radar to more input data. So also include satellite imagery, lightning, blending with potentially or surface stations, and get more of the variables, so not only precipitation, but also wind, temperature, clouds, and generate probabilistic ensemble nowcast. So the first step is to choose which of the many AI algorithm to pick. And there's really a trade-off between performance and complexity. So from top to bottom, it goes in increasing complexity, but also increasing performance. And the color code is, green is better, and red is worse. So if you go on the top, RayNet, it's only radar, pretty light training, and everything is ready to be used, but the lead time is not much more than pi steps. And then if you go on the other extreme, MetNet 3, which using vision transformer with CNN and using many inputs, radar, satellite, 1 hour forecast from her, and 1 minute stations, the GPU usually is extreme, and actually there's no code, it's not open at all, but the lead time is 18 hours. So because there's some commercial interest, now Google will provide or this kind of forecast is already available in US and Europe, but we don't have access either to the code. So there's some clones. So some people try to do the same, but there's no open source code for that. So then we looking at the different options, we chose to work with nowcastnet, which is a bit lighter on the GPU usage, still a very good performance and accuracy, and population nature, and then get open source code with inference and checkpoints for pre-trained model. So nowcastnet is essentially a GAN, like a generative adversarial network, with some other bell and whistles. That is some advection part, which create a kind of a physics hybrid, if you want, because it also part of the model that will advec the radar and learn how to do the good advection and correct for intensity. And so there's several neural network to train, and then it produce from past radar images produce future radar images up to 20 frames, so in a time step of 10 minutes. So the project phase, so wanted to start with something simple and go and increase complexity. So the first phase, which is already done, is to run the inference on a pre-trained model on ECC extraction data. And then the second phase is to retrain or fine-tune the model using ECC data. And the reason to do the fine-tuning is not necessarily to gain performance. I mean, we hope that it will do, but also to learn how to do it, so they gain knowledge. Also not to have to worry about any licensing issues, and to allow flexibilities if you want to modify the model to add new fields. And third phase is this move toward foundation models. This is where IBM is interested to use a foundation model to help to do nowcasting and probably help on the large scale forcing. And then the other phase are the stretch goals I already mentioned. So for the first phase of running reference on a pre-trained model, so the code is available, the checkpoints, the paper, there's a link, you can go there, download the checkpoints, use PyTorch, and it can run things. And then for sure there's some effort to do data processing, but once it's done, it works. And so we did that. We get the radar target. So this is from a precision composite. And then we do nowcast for 10 minutes and also for 70 minutes. So we did for different time steps and see that it looks reasonable. So the second step is to do the retraining of the model using ECC data. So we de-archive radar precision composite. So 1 year of data at a 10 minutes interval, which is the same as what nowcastnet is using. So basically it's data before the radar upgrade to 6 minutes. And so actually the data is available. So anybody can want to train their own model, or the data is available for all to use. And as a preprocessing, we upscale from 1 kilometers to 2 kilometers, converted to a ZAR format for more efficiency in the training. And then we created a private GitHub repository for collaboration between ECC and IBM. And for the inference, it can run on GPUs, and eventually we'll make it also work on the CPUs for if the GPUs are not available. So the GPU we have is a A100 with 40 GB of RAMs. And then for training, actually, it's a bit heavy. It was trained by IBM. It's a 800 GPUs. It took about 5 days to train.
Dominique, 2 minutes.
Okay. So I want to go to the results. So there was some challenge. It didn't happen like just take the model, run it, train it. There was some issues like about part missing, that the training code was missing. At first, when the first iteration, there was some artifacts, but at the end now we got something that looks at least to the like eye candy test. So on the left is the reference, and on the right is the nowcastnet that we fine tune on data. And then the version is not done yet, but visually it looks okay. So that there's no like big artifacts that we don't like, and actually even some of the artifacts from the radar are removed. So there's some interference from the radar that is part of the data, but the model learned to remove these artifacts. So I don't have time to show all the examples, but for sure there will be more time to do a thorough validation. But it looks that it does something, and doesn't only add VEC, but also some of the radar echo are like there's some dissipation of the storms. There's no initiation. I don't think it's working, but there's a dissipation after a few lead time. So the next step will be to couple with a large AI model. So we'll discussion with IBM to see like where we can put it. A bit of issue now because nowcastnet is a bit larger than we thought, but we'll do that. And then I see Miguel, so I have to finish very soon. But I leave with my conclusion. Basically, we experience it's positive to learn working with IBM and publishing using published model on CADA, but open source is sometimes it's more complex than just taking the code. So the experience we learn. And if you want this reference here, thank you.
Merci Dominique. J'ai une question pour toi. Je vais te la donner en anglais. Is the AI-based nowcasting very different to the AI-based longer range forecast?
I would say yes and no. So these differences. So if you look at the resolution for the nowcast, it's high resolution. We are learning directly from the data. We're not using any data simulation. But the techniques can be very different, very, very similar, like using a vision transformer or diffusion model or GAN, both can work. So it's similar in this way. And so I don't think there's a fundamental difference. So the skill at learn to do longer term forecasts is the same as nowcasting.
Merci, Dominique. You're popular. There are more questions, but we don't have time, unfortunately. I have to turn the screen and the mic over to Vikram Khade. He's a physical scientist from Environment and Climate Change Canada. His presentation is entitled Investigation of a Deep Learning-Based Simulator to Increase the Ensemble Size in an EnKF with the Recentering Technique. Experiments with the Lorenz 1996 model. So Vikram, I see you're all set. So I'm going to hand the mic over to you.
Is my screen visible?
It is. Looks good.
Okay, thank you. So hello everybody, my name is Vikram. I work at MSc Montreal. The title of my talk of investigation of a deep learning based simulator to increase the ensemble size in an EnKF with the recentering technique, experiments with the Lorenz 1996 model. Ensemble Kalman filter, EnKF, is a data assimilation technique to combine a prior, also known as the first guess, with observations along with their errors to obtain a posterior update, which is closer to the truth. Apart from the mean estimate, it also gives the uncertainty in the posterior. EnKF involves running a short-term ensemble forecast of the model to obtain the prior. The root mean square error, RMSE, in the analysis decreases with increasing size of the ensemble. As the size increases, it saturates at some point, but in general, the RMSE is inversely proportional to the size of the ensemble. Typically, the ensemble size used is small because it is computationally expensive to run model forecast. This results in a noisy estimate of the covariance, which is calculated using the ensemble. The covariance estimate plays a key role in updating the variables and their uncertainty. Localization is used in an EnKF to ameliorate the noise in the covariance estimate. This localization is distance dependent. It is a weight which decreases as one moves further away. Deep learning DL simulator can be trained to simulate the forecast model, and then it can be used to run multiple forecasts. Typically for real models like ECC's GEM, training a deep learning simulator is very expensive, but running a trained model is relatively cheap. So you can find a reference here. It is not for GEM, but for some other real model. Increasing the ensemble size using a DL simulated model would allow for a longer localization radius. This can improve the balance and reduce the RMSE since each observation will update variables out to longer distances. In this work, I demonstrate that ensemble size in an EnKF can be efficiently increased using deep learning simulator, thereby lowering the RMSE in the Lorenz 1996 model. Larger ensemble size have a potential to provide better probabilistic information about extreme events. This is the equation that defines the 40-dimensional Lorenz 1996 model. The xi's are the components or variables. I goes from 1 to 40. Therefore, the dimensionality D is 40. F equal to 8 is the forcing. And 0.05 time units in the Lorenz model is equivalent to about 6 hours in the atmospheric model. We can figure this out by doing error doubling experiments and find out the error doubling time in each of the two models and come up with such a comparative time scale. This model has been used by many researchers as a test bed to try out new data assimilation schemes, improvements to the data assimilation techniques, etc. So this model is very useful because it looks like the atmosphere. And rather than trying out a new technique with a full-blown model, it is always good to ask the question whether the technique improves the data assimilation in a low-dimensional model. So that way you don't waste a lot of time just in case your technique fails. And also you can find out the basically the pros and cons of the new technique that one is proposing. So that's the motivation behind starting with the Lorenz 1996 model. So Lorenz 1996 model is a stripped down or a minimalist version of the atmosphere. It has a advection term, it has a diffusion term, and it has a forcing. These 40 components can be thought of as a dynamical dynamic variables around the latitude circle. Deep learning simulator for training of L96 simulator. I generated 10 million 6 hours lead forecasts using L96 model. What this means is that I simply used numerical integration to run the L96 equation, to integrate the L96 equation for a very long time. And then from that, I obtained samples. So these samples, 10 million 10 million initial conditions, are located in various parts of the phase space of the L96 model. These data are predictors and predictant, where the predictor is the initial condition and the predictant is the forecast after 6 hours. I then use this data to train a DL-based simulator for L96. 70% of the data are used for training. The remaining 30% are used for validation. So I have 40 neurons in the input layer. So this figure is not accurate compared to what I have done compared to my architecture. So there are 40 neurons in the input layer, 40 neurons in the output layer. The input layer is basically the initial condition with 40 variables, and the output is 6 hours later forecast for the 40 variables. And I have used one hidden layer with 2000 neurons with the sigmoid activation function. Here is the deep learning loss curve, and as you can see, there is a small. Actually, it is very hard to see, but this small error is non-zero, and it is a simulation error present in the DL deep learning simulator. Training and validation errors are comparable, so there is no overfitting. After the training is completed, the DL simulator is saved. The saved simulator basically contains all the optimized weights. Then the DL simulator is faster by a factor of 3 in executing the forecast compared to the numerical integration of L96 equations. Here is the setup of the ensemble Kalman filter, EnKF. So DA1, DA2, DA3, etc. are the data transmission cycles at which point the update happens. So starting from the posterior of the DA1, a forecast is launched, and ensemble forecast is launched of n ensemble members using the numerical technique in the integration. An observation system simulation experiment setup is used. Observations are drawn from a true trajectory. So we have the observations 6 hours apart. So as soon as the observation is available, the prior is combined using the EnKF equation with the observation to obtain a posterior, and again an integration is launched, a forecast is launched, and so on. Perturbed EnKF is used. Every other component is observed. Therefore, M equal to 20 out of D equal to 40. So I'm observing component number 1, 3, 5, 7, and so on. H is identity, the observation operator's identity. R is 1% of the attractor size, which is the observation error. Attractor size is the average standard deviation over all the 40 components, which is used as a kind of to normalize the error. 2000 DA cycles with assimilation every 6 hours is used. The very well-known Gaspari cone localization is used for a given ensemble size NNs. I ran tuning experiments to determine the best value of localization radius. Here is the setup of the mixed EnKF that I am proposing. So the setup is the same as for EnKF experiment, except a subset NDL is integrated using the DL simulator. So NNs is equal to NMD plus NDL. So the yellow lines are the NMD ensemble members, where MD just means basically model, while NDL, the magenta lines curves are the ensemble members that use the simulator for the forecast. At every DA cycle before carrying out the update, the DL sub-ensemble is recentered on the mean of the NMD sub-ensemble. This step is very important. Without the recentering, the mixed EnKF does not give a good result. Several EnKF experiments are carried out with different sizes of ensemble, NNs equal to 10, 20, 40, and 80. The analysis RMSE from these experiments provide a baseline. Several mixed EnKF experiments are carried out with two different values of NMD. So the subset size NMD I changed twice, so two different values to run different experiments. So here are the results. So on the y-axis, I have got the RMSC analysis RMSC. On the x-axis, I have the ensemble size of the experiments NNs. So I ran experiments with NNs equal to 10, 20, 40, and 80. The black curve is the curve which uses usual EnKF, and therefore it provides a baseline for comparison.
Vikram, 2 minutes.
As you can see, for NS equal to 10, we have RMSE of 0.5. So we see that for the mixed EnKF with NMD equal to 5, the red curve, when NMD equal to 10 and NDL equal to 10, ensemble size is doubled compared to NS equal to 10, decreasing the RMSE from 0.51 to 0.38. For NMD equal to 10 and NDL equal to 70, ensemble size is increased by a factor of 8 compared to NNs equal to 10, decreasing the RMSE from 0.51 to 0.31. NMD equal to 10, that is a red curve, provides a better approximation to the baseline compared to NMD equal to 5, which is the blue curve. With NMD equal to 5 and NDL equal to 75, the RMSE diverges, so we cannot go on arbitrarily adding more and more ensemble members. The recentering corrects the simulation error in each NDL ensemble member. This allows the mixed EnKF to take advantage of the better covariance estimate calculated using the higher ensemble size to arrive at a lower analysis RMSE. The divergence seen with NMD equal to 5 shows that there's a limit to how many DL ensemble members can be added to lower the RMSE. This limit depends on the value of NMD. Conclusion, a chaotic dynamical model can be simulated using a DL network given enough data. The mixed EnKF with recentering of the DL sub-ensemble approximates the analysis RMSE of the pure model ensemble. This approximation is better for higher value of NMD. Doubling the ensemble size from 10 to 20 in the mixed EnKF decreases the RMSE by 25% for NMD equal to 10. Despite the simulation error in each DL ensemble member, the improved covariance estimate due to larger ensemble size allows the mixed ensemble to perform well. This is possible because the recentering corrects the systematic error. These results demonstrate that the ensemble size in an EnKF can be increased efficiently by using a DL simulator for the forecast of a subset of the ensemble. The efficiency comes from the fact that a trained DL model runs very fast compared to the numerical integration, though the one-time cost of training a DL model can be high. These results raise several questions. What is the sensitivity of the result to the DL simulation error? Separate DL simulators can be trained with more or less data to answer this question. How good is the approximation to the baseline with NMD equal to 1? How well do the spreads compare? I only showed RMSE over here. Do CNNs simulate L96 forecasts more efficiently than a DL network? What is the sensitivity of these results to observing fewer components or non-identity observation operator? Lastly, do this conclusion hold true for higher dimensional models such as a QG model? Thanks.
Thank you for this talk, Vikram. I was wondering if you could elaborate maybe on your last graph, because I was surprised at the fact that, could you elaborate on the number of members that adding more actually increases their MSC?
Yeah, so there is a simulation error in each of the ensemble members. Now, this simulation error has two components. There is a bias and a random error component with respect to the mean of the model ensemble. So by recentering, we are getting rid to a large extent the systematic component, but the random error still stays. And as the population of the simulator ensemble members goes on increasing in proportional to the ensemble members coming from the model, it becomes harder and harder to keep the RMSE low.
Okay.
So there is a optimality to it.
Merci, Vikram.
Thanks.
Thanks, Vikram. Now I'm really pleased to present Jill Psotka from the University of British Columbia. She'll be presenting on extending the skillful range of hub height wind forecasts using self-organizing maps. So Jill, please do share your screen. And I'll turn the mic over to you now.
Okay. Hi, everyone. I'm Jill. I'm a master's student at UBC, and I'll be presenting my research on extending the skillful range of hub height wind forecasts. So this research is focused on wind farms in BC, but the hope is that this method could be applied anywhere. So there are 12 operational wind farms in BC, indicated by these green circles on the map. And together they contribute 4% of BC's electricity production, the most of which comes from this group of wind farms in the northeastern part of the province. And with wind energy, power companies use wind forecasts to balance energy supply and demand. So, for example, in British Columbia, our main source of energy is hydroelectric dams. And BC Hydro, who's the main power company, they use wind forecasts in order to help make decisions about the water levels in their reservoirs so that the wind energy and hydroelectricity can complement each other. So the better our wind forecasts are, the more efficient the entire power grid becomes. So the specific question that we're focusing on in this research is that numerical weather prediction forecasts of wind speed do not have much skill past 6 or 7 days out. So this is an example of a probabilistic wind forecast that we would provide to BC Hydro with lead time on the x-axis, so it is 1 week into the future, and then wind speed on the y-axis, which is directly related to wind power. And we can see at the very beginning of the forecast, when we're forecasting for tomorrow, the distribution is a lot narrower, indicating that we're more certain about what the wind will be, versus by day 6 and day 7, the distribution's very wide. And at this point, this forecast isn't really telling us much at all about what will actually happen. So the first question we asked was, do any forecasts related to wind speeds have skill past 7 days that we could then use? And looking through the literature, a very clear answer was geopotential heights. So since geopotential heights are a larger scale variable, they have less variability in time and space compared to wind, which is sporadic. This makes them better at forecasting at longer lead times into week 2. And also geopotential heights at various pressure levels have been shown to correlate to hub height winds by various other studies. So then our question became, can we use geopotential height forecasts to make wind forecasts? And there are a lot of ways one could go about trying this, and we decided to go with self-organizing maps. So this is an unsupervised machine learning technique where the input layer consists of many input vectors that are all the same size, and the output is a 2D map of neurons or nodes where each node is the same size as an input vector. And to train the self-organizing map, you first initialize the nodes, and then for each input vector, you find the best matching node. And this is where competitive learning comes in. So that best matching node and its neighbors update themselves to be more similar to that input vector. And you do that for all the input vectors multiple times, and you end up with a trained map where similar patterns are beside each other. And this is often used for reducing dimensionality and clustering, which is what we use it for. So the way that we're implementing self-organizing maps is using past patterns of geopotential height anomalies. So we used 11 years of reanalysis data from ERA 5, and our input vectors are these grids of geopotential height anomaly that are centered around the wind farm. And then when we put this 11 years of data into the algorithm and we train the map, this is an example of what a trained map looks like. So this example is for 6 hourly average geopotential height anomalies in the summer months at 100 kilopascals, so close to the surface. And we can see here that the negative anomalies tend to go towards the right side of the map, and the positive anomalies tend to go towards the left side. And every node has a slightly different pattern of geopotential height. So after we've trained the map, we then cluster that same input data based on their best matching nodes. So again, the input data are these grids of geopotential height anomaly, and we can calculate the best matching nodes just using Euclidean distance. And this essentially sorts our input data into clusters. And this is where the wind comes in. So for each input vector, we have an observation of wind speed at the wind farm of interest. So when we're clustering these geopotential heights, we're effectively also creating clusters of the wind speeds that happened. And this creates distributions of the winds that happened associated with each node. And we can see here that the windier patterns tend to be towards one side of the map, which is good news for us because that means that the geopotential heights, the nodes that we've created, are correlating to the winds because we're seeing patterns. So that's like the training and setup of the method. And then to actually do the forecasting, we take a geopotential height forecast, we calculate its best matching node in the trained map, and then we can use the associated wind distribution as a probabilistic forecast. So the data that we used for this method was, as I said, 11 years of reanalysis data to train the map. And then we have hub height wind observations at a wind farm. And these need to span the training data as well as the validation and testing years, which was 3 years. And then you need geopotential height forecasts, which we use the American Global Ensemble Forecast System. But because this whole thing is trained using reanalysis, you could really use any forecast of geopotential heights and you wouldn't have to retrain at all. So then the final question becomes, does this actually work? And there are a lot of ways that you can evaluate how well a forecast does. So looking at probabilistic metrics, so how well does that probability distribution forecast the wind? And all of the plots I'm showing are for 24-hour average forecasts in the summer using 100 kilopascal geopotential heights. And we have lead time in days on the x-axis, so this is during week 2, and the skill metric on the y-axis. So starting with continuous rank probability score, this is like mean absolute error if it were for a probabilistic forecast. And this is a skill score, so it's comparing to a reference forecast, which is just climatology. So how well a climatology forecast would do is on the 0 line. And we can see here that our method in blue is skillful compared to climatology until about day 13, whereas the regular way that GEFS would forecast 80-meter wind does not have any skill at all during week 2. And secondly, the Breyer skill score for the 50th percentile. So this is how well does the method do at predicting winds either windier than average or less windy than average. And you can see again, our method is skillful until about day 11, whereas the regular way of forecasting wind does not have skill at all during week 2. And then we can also look at deterministic metrics. So to do this, instead of using that whole probability distribution as a forecast, we just take the ensemble mean, and then we compare that to the observations. And here we have the mean absolute error of the ensemble mean. And we can see here that, again, generally our forecast is better than climatology until about day 13, whereas the regular GEFS forecast has significantly less skill. And then finally, the bias of the ensemble mean, we have similar bias to climatology, which is just a slight negative bias, whereas the GEFS wind forecast has a pretty significant negative bias. So in summary, we're trying to get longer range wind forecasts so that we can improve wind energy efficiency. And we're doing this by leveraging the lead time advantage of geopotential height forecasts to try to create wind forecasts. And preliminarily, we have improvements to wind speed forecasts in the 6 to 12-day range, at least for the summer months. And this is ongoing research, so next I'm testing other seasons, testing different time resolutions, and also looking at the robustness of our verification metrics and results. So thank you for listening, and I also wanted to thank the funding sources for this project, and I'll take any questions.
Thank you, Jill. For once, we have time for questions. Congratulations. I have a couple of questions. So my first one would be, well, the results that you have are pretty impressive. Were they used by the wind farms, or were they looking for integrating your result as soon as possible?
Yes, so we are partnered with BC Hydro, who is the one who would use these wind forecasts. And the idea is that hopefully within a few months, we'll be able to integrate this into operational stuff. And they're already using the GEFS forecast, so they have the geopotential heights downloaded, so it wouldn't take much operational time at all to implement this.
Okay. I have one online for you. So why would climatology have a non-trivial wind speed bias? Were the test years anomalous? Yeah.
That's a good question. I didn't think about that. Let's see. Yeah, so the climatology that we're using are all of the wind speed observations that we had from training. So that was 2009 to 2020, and then the test years were 2022 and 2023. And I'd have to look into the slight negative bias. I kind of wrote it off, but that's a good question.
Merci. Another one. I may have missed it, but what is the temporal resolution of the input data to train the map? And what are the implications for the wind forecast data, which look to be sub-daily?
So the resolutions for training the map is 6 hourly, which is the resolution that we have for GEFS forecast past 10 days. And then I'm looking at testing different time resolutions for forecasting. The idea being that the more desperate you get for an accurate forecast, the longer you have to average for. So these results are for 24-hour averages. And I also looked at 6-hour averages for forecasts in week 2, but the results were just messy because they depended on time of day. So these were just prettier plots to show.
Noisy, I guess.
Yeah.
We have another one. Let me see. I am wondering, while choosing a reliable long-term forecast item as geopotential height, what other items have you guys explored and considered?
So we chose geopotential heights because that's what the literature was doing. So there's a lot of literature that's finding correlations between geopotential heights and hub height winds. But to my knowledge, there's no one that's actually using this to forecast. So that's why we chose geopotential heights, to base it off of the literature. But we'd be definitely open to trying different inputs as well.
Okay. We still have time for another one, so people are writing questions as you answer them. How would you define robustness? How would you measure it?
So that's something that I'm actively looking into. If we're talking about the robustness of the statistics that I've shown, I'm not positive how I'm gonna do that. Definitely because I don't love how spiky these statistics are, especially for GEFS. It looks a little weird. So I've started looking into the distributions for the statistics. I started looking at plots like this where it's showing the exact same data, but instead of showing the mean of the statistic, it's showing the whole distribution. And I think this kind of shows better how robust these statistics that I'm showing are, but I just made this this week, so still working on it.
Okay. One last one. How does the system work on shorter time scales? Because your graph starts at day 6. So how does it behave?
I'm really not sure. We were only interested in forecasting for week 2 winds because we just assumed that a regular wind forecast would be better at shorter lead times. So I was planning on only looking at starting day 7 to 14 and just including day 6 as like a reference point, but then day 6 also ended up being better. So I'm not sure how well it would do closer to day 0.
Maybe you're better than the official system. Maybe you could look.
Yeah.
Over to you, Anne.
Jill, that was a great presentation, and I also want to congratulate you on your presentation skills. They're very impressive. So now we're going to have to move on. So we're going to welcome Jonathan Gadoury. He's from Intact Financial Corporation. He will be presenting on using machine learning to model severe weather risk in insurance. Promises to be interesting. So over to you, Jonathan.
Hello, do you see my screen and can you hear me?
I see your screen and I hear you. All's well.
All right, perfect. Thank you for the introduction. I'm Jonathan Gadoury. I work at Intact, and I'm going to talk about more in a general terms how we can use machine learning to model severe weather risk in insurance. So I come from the atmospheric science background. I'm not a insurance guy initially, but that's kind of where I ended up working. So I'll just first introduce Intact, what it is, and the kind of goals that it have regarding weather and climate change, and how our team can try to support this by different projects. So I'll go in a bit of details into some of those projects we've been tackling in the past few years, notably how we can kind of try to better segment risk, for example, wildfire risk. Also some other projects that have been using machine learning to try to better capture some patterns in our data, mostly weather and insurance claims data as well. So Intact, if you're not aware of the name, is basically the biggest property and casualty insurer in Canada. And the main purpose, as our corporate people identify it, is here to help people, businesses, and society prosper in good times and be resilient in bad times. So really puts the context of severe weather into it. Of course, that's what causes the most instability to insurance companies. Weather is highly variable from year to year, and of course, it's bound to be changing because of climate change. So that's where we're kind of trying to use atmospheric science skills to better understand the risk. So mostly what we insure is homes, automobiles, and commercial buildings. And just to kind of give a bit of introduction to our data science team. So Intact is pretty big, and we have about we have a team called the Data Lab. We're about 500 people into it, a mix of data scientists, AI engineers, data specialists, and we have university partnerships as well with a few universities across Canada. So basically, we put a lot of resources into it with the objective of try to be the best AI shop in the world regarding the insurance industry. So not just Canada, but the world. So for us regarding climate, what is interesting is that in this whole data lab team, there is a smaller team called the Center for Climate and Geospatial Analytics. And our goal is basically to try to support the climate strategy that Intact has. So there's a lot of things regarding trying to be carbon neutral, trying to collaborate with governments, and enabling transformation of the industry towards a greener economy. But for us, it's more about good risk segmentation. We're trying to have a competitive advantage with price, with better understanding the risk and how we can have accurate pricing. Also supporting adaptation and mitigation by understanding where are some areas where perhaps we should try to support communities being better prepared against climate change. So that's kind of where our team tries to fit in, is to try to basically support different business units with information, and ML can be really helpful for this. So for example, for wildfire maps, something that it's one of the severe the many perils that we can try to model. It can be it can be hail, it can be heavy rain. Wildfire is one of those that is a lot more popular lately. And it's kind of it's something that is not very available on the market yet. So we kind of have to generate those maps ourselves. So basically, we need to take a bunch of open data, either it's topography, either it's climate data, drought indices, fire weather index, things like this. So for the weather and the fuel components, you can use data on road networks, campsites as well, just for fire ignition, for example. And basically what we do is we try to take all of this.
You're fading out, Jonathan. On a de la misère à t'entendre.
I'm fading out. Est-ce que tu m'entends là?
Ah, c'est plus t'es proche, mieux c'est.
Okay, I'll try to speak a little bit closer to the camera. So we can, so I don't know how far back, but basically we just need to, we're trying to have a lot of good variables. And then what we try to do is, since most of our projects, we don't have the luxury of spending a whole PhD's worth of time on developing, maps or projects. Usually we kind of go rather quickly, and that's where machine learning can kind of really help us to try to go from those features to something that can be useful. So, there's different modeling techniques we can use. Traditionally, we were using something called generalized additive models, but now we're kind of mostly going towards gradient boosted trees on neural networks. And our wildfire map we generated in 2016, we kind of used those three and generated an ensemble of predictions to kind of get a map that shows that highlights the risk across Canada. And this is something that we're kind of bound to update soon enough, now that more data is kind of getting, more updated data is becoming available to us. Another example of project we did was to try to better understand the risk of sewer backup. So what we mean by sewer backup is when there's a lot of heavy precipitation, and basically the sewers get overloaded with all the storm rainwater, and basically if you have a defective backwater valve, or there's too much water, it can penetrate in your basement through the shower or through the toilet, for example. But the thing is that what was happening is that generally you would expect your sewers to be able to capture regular rain events and just lead to sewer backups if the return period of the rain event is maybe, I don't know, 20, 25 years. But the thing is that we noticed that there were a lot of floodings from very relatively weak thunderstorms. And we're just wondering, okay, well, of course the hazard plays a part, but is there a vulnerability component that we're not properly capturing? Can we actually try to capture that level of risk? And there's not that much data you can find on the sewer infrastructure. Some cities make that data available, but definitely not Canada-wide, that's for sure. Oops, sorry. So basically that's kind of what the angle we were trying to go to, is that can we try to use our own sewer backup claims data and try to kind of come up with some variables that would help us try to assess, are there some areas that are more at risk of sewer backup, and basically try to identify a proxy for the infrastructure that we don't have the data from, because it varies locally. It varies by depending on which year it's been implemented, which year has it been repaired. Does it account for more recent climate? Is the infrastructure kind of not working properly? Is there more increased population in a particular city that would lead to more rain in the sewers? There's a bunch of factors that kind of go into play. And since rain is actually or flooding in general, just any water peril is actually what's causing the most damage to intact, there was really a need to try to better understand this. And we're really trying to go at it from a perspective of, we're not just looking at the weather itself, but we're looking at generally we look at the weather and the exposure. So your house, what it's made of, is it 2-story, do you have a garage, and things like this. But now we're kind of trying to add the component of vulnerability itself, more like maybe at a neighborhood level. So there's a bunch of variables that are available that we can use. to try to basically represent or reflect the the socioeconomic risk. No, I'm showing a lot of variables. Not all of these can be used in the insurance models, just of course because of potential biases. But for example, from the census data, we can use a lot of publicly open variables and try to hopefully get a sense of there's some factors in there that would lead to potentially a more vulnerability to rain. And what we actually notice is that the model we generate, if we apply the prediction and we look at let's say the Isle of Montreal, the hotter colors are basically an increased chance of sewer backup, and we compare to publicly available figures for the Montreal infrastructure for sewers, where there's basically two different types of network. I mentioned.
2 minutes, Jonathan.
Yep. So there's either the one that has a pluvial the pluvial network. So it's so you have the sanitary and the pluvial separated. Coincides quite well with where we have lower risk. Well, if there's higher risk, it seems that it's the unitary drainage network. So it seems that even without using any sewer data, we kind of our model seems to capture some patterns, and this is basically machine learning model between features and our claims data. And also as proof of concept, we're trying to see, can we kind of use similar approaches to actually predict how our claims data is going to change because of climate change. So basically what we did is we took a lot of climate projection data. We derived some climate variables, and I'll just kind of go to the next slide. And basically just by using I think it was CMIP5 data at the time. Yeah, CMIP5. Just with temperature and precip, we calculated a lot of relevant variables for us. Usually, try to kind of convert it back to snow, days of snow, and things like that. Anything that would indicate increased risk of accidents on the road. So basically, we took 5 years of data, of our claims data. We looked at some major cities in Canada, and again, we trained a model on this. So basically, with these features as inputs or claims as target. And what we actually notice is that when we apply the prediction to the entire window of the claims data of the climate data, we actually see a decreasing trend around 2040 for the city of Toronto, for example, for this specific peril, which there's a pretty sharp decrease in auto accidents that is expected. So that's maybe one of the only good things for insurance companies regarding the climate change is that, well, we might expect less accidents, but probably everything else gonna go up. So just to conclude, machine learning has a lot of applications in insurance. It allows us to bridge, make a bridge between our claims data and a lot of weather observations or climate projections. And I just want to emphasize that for us, open data is really critical to us to kind of allow us to make those kind of internal models. Just because we're not taking any observations ourselves. So yeah, but it's a challenge being in a corporate world. We're not always don't have access to everything, but we're trying to do what we can with what we have. So thank you.
Merci, Jonathan. So we'll take all the good news that you have regarding climate change. If you have any other one, throw them at us. I have a couple of questions. First one, how do you balance not overpromising the results when you try to model at scale? I understand the variation in municipal data. Maybe some things shouldn't be in your prediction pipeline because you cannot get the data and the proxy data is insufficient. Also, this is as potential racial biases.
Yep, no, of course, and so that's when I showed the list of variables. That's kind of the data that was available, but we're not using anything that would lead to any racial bias or anything that would be unethical. All the internal models actually get reviewed, get validated by external committees, just to kind of limit the potential to this. And can you just repeat the first part of the question?
How do you balance not overpromising the result when you try to model at scale?
Yeah, actually, we're kind of, we don't need to overpromise, or I think we're in a situation where anything helps. So because we work a lot with actuaries, they have absolutely no idea how to use this kind of information. So you would say an increase of 5% for Canada, for example, for specific peril, that would already be beneficial to kind of make informed decisions as to how we manage the company, how we manage the risk. Of course, we want to be a lot more granular. So yeah, I don't think we're over promising anything. I think it was just kind of anything we give is already kind of added value.
And finally, one last question that is dear to my heart. Our radar data would be important for you, especially if it was open.
Yes, well, actually, I did purchase radar data in the past, and where Saladin was my best friend, and it was just too difficult for us to access, for sure. At least on terms of research perspective. I know it's been a few years. I believe that the way that the data is shared now is different on the ACC side, but it could help. It's just that on our team specifically, we're not focused on the current risk. Mostly, we're not kind of looking at short-term forecasting. So if we were to train a model, we would need to kind of use all the radar data, which would be quite a lot of data, because we're ultimately trying to look ahead and predict risk, not kind of anticipate the claims for the next day or two. That's kind of not our realm of expertise.
Merci, Jonathan.
Thank you.
Thanks, Jonathan. So we're moving on. Last but definitely not least, Renee Sieber from McGill University. So Renee will be presenting on analyzing public engagement with official weather alerts in northern climates to develop new computational approaches to improving communication. So Renee, if you want to share your screen.
Hold on one moment. Thank you. Sorry, I'm experiencing considerable lag at the moment.
So am I, Renee. So it might be a generalized issue.
If you just make sure that you don't have a tab that's unmuted right now.
Sorry, are we okay?
I can see your screen and I hear you properly.
Okay, great. Okay, sorry about that, folks. So, weather information conveyed through official alerts is aimed at enhancing preparedness and situational awareness. And we've looked a lot at forecasters and crisis managers, but less attention has been paid to how the public engages with weather messages, especially regarding winter weather, and how AI can be used for more than NWP. So I'm really happy to be joined by my colleagues at McGill University, Mount Washington Observatory in the US, MILA, the Quebec Machine Learning Institute, and this project is funded by Environment Canada. So we're trying to look at the engagement of lay public and experts with top-down broadcasting of weather information on social media. And this is a break with the top-down classification schemes predominant in the crisis informatics literature. So we're trying to propose an agile bottom-up approach to analyzing weather information, and we're using artificial intelligence classification methods to look at the complex relations Canadians have with cold weather, whereas the crisis informatics literature emphasizes earthquakes and floods. So how did we start this? Well, we looked for Canada-specific training data sets in English and French. This is by no means trivial, in part because Francophones don't use Twitter or X nearly as much. But Twitter is the predominant social media platform for looking at social media engagement. For English, we focused on official sources, specific area message encoding alerts. That's the form of environment Canada notices, and they're bilingual. They are bot-driven. And we're also looking at official hashtags XX, WX, so ONWX. And this is to encourage people to share and engage with weather information. And for the French, we looked at the same alerts and the hashtags, but we only got 2,000 tweets. So to create a larger sample, we scraped French tweets with general weather terms. We actually got 100,000 tweets in response, and we narrowed that down to 30,000. So engagement with official authoritative content was an important first step with us because we wanted to know whether people actually were engaging with official content. So by engaging, we operationalized that as replies, quotes, retweets, and likes. And these interactions serve as a proxy for activities related to weather impacts. And as I've noted in past communiques, when you're working with social media data, you take what you get in terms of engagement, and these are the best proxies we have for social media engagement. So in case you're interested, what do people listen to? They listen to storm warnings. Compare that to how little they listen to winter weather travel advisories. And they like the tweets. So that's a minimal level of engagement, but they're liking tweets as compared to, say, retweeting them or quote tweeting them. The bad news is that there are very few interactions among the public and experts as well with official content as well. So 70% completely no interactions with SEAM alerts, and over half no interactions with official hashtags. Although the silver lining of that is that if they are listening to official content, they are listening to experts more than to each other. So they are heeding official weather information. So now we're moving on from what people are listening to what topics are they interested in. So we used NLP, natural language processing, to develop a classification scheme for people in Canada impacted by winter weather, which differs, as I mentioned, from traditional crisis informatics schema trained on earthquakes and floods. We've actually used a lot of NLP methods in the 6 years we've been working on this project. And even in this project, we have used unsupervised classification, supervised classification, and then we moved on to foundation models. Each one of these requires different amounts of data, training data. So this may be a little bit hard to read, but I just wanted to give you a sense of what people were interested in when they were engaging with these winter weather or weather-related tweets. And you can see there's a fair amount of questions about driving safety, schools. There's also lots of recreation with dog pictures. This next slide will give you slightly better image of what people were interested in. Lots and lots of recreation related tweets related to birding and dog pictures. I love the colloquial posts that are related to storm chips, for example, by going out and buying chips because a storm is coming. We're most interested in the impacts related to winter weather, like power outages, school closures, snowed under cars, snow plows, and shoveling. We're also interested in neighbors helping neighbors. So we went through many iterations of the following taxonomy to derive a taxonomy for winter weather that we tried to mirror as much as possible with the traditional crisis informatics literature of Imran et al. And this is what we came up with. We had various, I can't even think about how many unsupervised classifications we ran to come up with this. I want to point you to the following two categories: service interruption and remediation. One of the goals of this research is to respond to the prosaic nature of snow in Canada. So much of the crisis informatics literature is based on extreme acute events, and we're interested in the day-to-day effects that may not be extreme, but are incredibly disruptive to our lives. We can deal with it. We have the infrastructure, but it still impacts us. So we then focused on, so we needed a lot of unsupervised classification to come up with that taxonomy. We want to use a taxonomy for supervised classification where you get these buckets. You saw those buckets in the rows, and the untrained data gets put into those buckets. But you need a lot of training data to tune your supervised classification. And if you do crowdsourcing, which we did, and if you use quasi-experts, which we did, it can cost a lot of money. So and it takes a fair amount of time to do it. So we were looking at ways in which we could speed up the training data creation for supervised classification. So we went to foundation models. Just want to say that the Meteorological Service of Canada has been funding foundation model work since 2018 with our project, because we've been using BERT since 2018 when it was announced. So this is an example of a prompt that we gave to GPT-4 to create our training data. And you can see the prompts. We had to do a lot of prompt training to come to this point. And you can also ask it to create a database. So we had it categorize content. This is the training data, and then put it into a JSON file. And to give you a sense of the sorts of things we came up with, and we reported on some of this last year, here's two examples of trained data. The top one is service interruption and remediation. The bottom one is on a resource information and remediation. One of the things that in which our research differs from traditional crisis informatics research also is we don't have mutually exclusive categories. We allow content to be in multiple categories. Okay, so we rely on automation to train our data. That can be problematic if you don't validate it in some way. So we actually created a very extensive intercoder reliability framework to validate the contents, the results coming out of GPT-4 to, for example, look at how much did the crowd workers, the quasi-experts agree with each other, how much did the crowd workers agree with the quasi-experts, how much variation in agreement was there by category, because some of the top categories in the taxonomy, what's the difference between a resource and a caution, is a lot blurrier than the difference between casualty and remediation. So what categories were more distinct and what categories were difficult. And we used Krippendorf's alpha for a lot of that. So in conclusion, just want to say that through this, we've created 2 repositories and as well as a classification scheme for winter weather using a variety of data collection methods. We integrated a bottom-up agile method and a top-down method through engagement with official weather messages. We used a variety of classification methods, unsupervised, supervised. I didn't mention that we also looked at one-shot, zero-shot methods as well. And we created a new model of validation on GPT-generated data to test the labeling, the automation of the training data. And thank you, and a special thank you to MSC for funding 6 years of this research. And that is it for me.
Thank you, Renee, right on time. I have a question for you. So you scraped Twitter, but well, first of all, how did you said that when it's time to look into social media, Twitter is the go-to place, but they've updated their policy in the last few months, I think, or year with it in the last year. So would that, did you gather your input before that, or would that affect what you would have done with this new policy? Does this make sense?
Yes, it makes sense. Twitter has updated its policies a lot before, during, and subsequent to our collection of data. And we have managed to stay ahead of all of it, and some of it requires a little bit more brute force than the use of the API, for example. But even with its methods, its proposals right now, we managed to be able to get some data. But
Thank you. I have another question. Have you also analyzed images associated with social media?
no, we are thinking about that, particularly as foundation models become much more multimodal. The problem with any of this data, and I presented yesterday on historical newspaper data scraping, the problem is token limits. The problem is this becomes expensive really quickly. So there are huge opportunities. So the short answer is no. The slightly longer answer is with Anthropic's Claude. There's much better integration of text to image and image to text generation with text to text generation. Oh my goodness, it is so expensive after a while. So one of the things we're doing is we're trying to investigate cheap methods to do this.
Merci, Renee.
Thank you, Renee, but thank you everyone who presented today. But thank you everyone who presented today, as well as all the attendees. I hope I'm not getting all the attendees. I had feedback on my end. I don't know if everyone can hear it.
Yes, Renee, do you think you can turn off your microphone? Thank you. Renee, do you think you can turn off your microphone? Thank you.
Okay, here we go again. Thank you all the presenters today. It was really interesting to see how things are moving very quickly. Again, next year, I'm sure you'll all have new things to share with us. Right, Miguel?
Oui, absolument. On fait ça chaque année. Là, c'est en ligne. Tout le monde est dans le confort de son foyer. Mais est-ce qu'on... Je sais pas ça va être où le congrès de la SMO l'année prochaine, mais on espère tous s'y voir en personne.
Alors,
on
à
fait
l'année
maintenant...
prochaine?
Oui. Merci tout le monde. Puis il va y avoir des enregistrements aussi qui vont être disponibles. On vous tient au courant. On va envoyer plein de courriels. Voilà. On s'en reparle.